was a challenge. Trying to understand how the eruption was going to progress was a challenge. We had lots of discussions about whether or not it was going to be an explosive eruption, whether it was going to be another dome-building eruption.
There is one way to find out. Analyzing samples of the lava might explain the mysterious solid blocks and what they mean for the future. At the Volcano Observatory, John Pallister compares lava from the spines with samples taken from previous eruptions. Could there be something in their composition that explains why the mountain sometimes pushes up spines, sometimes oozes lava, and sometimes explodes? Pallister begins with a sample of the lava that erupted so explosively in May 1980. He's immediately struck by the large areas of blue.
Okay, so what's important about this 1980 rock is the abundance of this blue area, and that's basically bubbles. Now, that's not a mineral. That's just open space in the thin section. That's where gas bubbles were. This sample would float in water. It had so much gas in it.
The gas comes from water, a component of the magma. As magma rises, changes in pressure turn the water into gas. The gas pressurizes the magma. It's what gives volcanoes their explosive force.
1980 had a lot of gas in it, so it exploded, tore itself apart in a tremendous explosive eruption.
But when he looks at lava taken from the 1983 period of dome building, it's different.
There is much less of this open space, of the gas filling space in the rock.
The 1983 lava behaves like a bottle of soda going flat. Finally, he looks at a sample of lava from one of the spines in 2005.
I don't see any blue space, any of that. Oh, there's just a little bit, but dominantly it is lacking in space. It's a gas-poor magma, except, in fact, almost none.
There's just enough gas to push it to the surface. But by the time it gets there, there's nothing left.
So this one came up slow, and it made sticky, solidified spines instead of making either lava flows or an explosive eruption.
It's a crucial insight. The amount of gas determines the nature of the lava and the force of the eruption.
It all comes down to the gas budget for the eruption. Is it going to fizzle, or is it going to explode?
Suddenly, the mountain's behavior makes sense. The spines are a sign the magma under Mount St. Helens is running low on gas. Then, in 2007, as if to confirm this new insight, the familiar drumbeat seismic traces vanish completely. No more spines appear. The lava below the mountain has finally run out of gas. How long will it take the mountain to build up enough gas pressure for another eruption?
I think that's the most important question we have to answer. How long does it take to build up the gas necessary to drive an explosive eruption?
That's now the question they need to answer. Geologists go back to the mountain to look for clues. The eruption in 1980 took the top off Mount St. Helens, leaving its history exposed in the rock walls of the crater. Most of the important previous eruptions are marked by different colored bands.
The lower part of the walls where you see gray and some yellows and some pinks, they're all part of the older edifice of Mount St. Helens.
These rocks, which make up the bottom half of the rock face, are around 16,000 years old.
Then if you look higher on the wall, near the top, you see darker colors. And those are rocks that began erupting about 3,000 to 2,500 years ago. So by looking at what we call the stratigraphy and this magnificent exposure of the rock types in the crater walls, we can piece back the puzzle and understand the history as far as eruptive activity at Mount St. Helens.
Do the rocks give any indication how long it takes to build up enough gas between eruptions for the sleepy mountain to awake again? John Pallister sorts and categorizes rocks from earlier eruptions. He checks notes and photos to try and determine how often the mountain has erupted violently. Drawing on previous records, he builds up a picture of Mount St. Helens' past. For much of the last 4,000 years, there seems to be a fairly clear pattern.
If we look at the number of big eruptions over the length of time the volcano's been active, you might say that there's one roughly every 1,000 years, a big eruption. So from our context here, we could say that it takes on the order of 1,000 years to build up enough gas to get a really large eruption.
The record suggests some of these eruptions have been huge. More than 10 times larger than 1980. Potentially enveloping vast areas of Washington and Oregon. But that would imply that the next really big one isn't due for about another century. Except for one little detail around 500 years ago.
In 1479 AD and 1482, there were two very large eruptions. So the volcano is capable of surprising us in producing two highly explosive eruptions in a span of less than 3 years.
Both these eruptions were much bigger than May 1980. There is no straightforward pattern. Mount St. Helens can pause for 1,000 years between big explosive eruptions, or it can pause for 3. These results have left geologists with one certainty and a number of questions.
First of all, we expect this volcano to erupt again. Has repeatedly in the past. There's no reason to think it's going to sleep in forever now.
There will be another eruption. But nobody can determine when or just how big it will be.
We don't know whether it's going to erupt explosively again in 2 years, or in 20 years, or in 200 years. That's an area that needs a lot more work, a lot more research to understand, and it is of fundamental importance to being able to forecast and to save lives and to save property.
For 30 years, Mount St. Helens has led scientists on an extraordinary journey of surprise and discovery. When they surveyed the destruction in the early 1980s, nobody could have predicted the speed with which life has returned.
It was another form of an eruption. It was an eruption of nature. nature marched back with a vengeance.